Professor Jean-Marie Lehn, Nobel laureate in chemistry, professor of the University of Strasbourg, Institute of Advanced Study, chair of chemistry of complex systems. In his presentation, Professor Lehn will offer insights into how chemistry provides the bridge and unravels the steps from molecules of inanimate matter and highly complex molecular architectures and systems, those which make up living and thinking organisms. He will expound on humankind's creation of science and the field of chemistry as the universe of all possible structures and transformations of molecular matter. Those realized in nature represent just one world among all the worlds that await to be created. Let us hear more on this fascinating concept from Professor Lehn, who will speak on steps towards complex matter chemistry.
Oh, that's my lab. Thank you very much, Bengt, for the invitation. You just reminded me that we started this series together, but we did most of the work. In 2006 it was started, and it was really a fantastic initiative you had. Thank you very much. Okay, now I will try to tell you where we come from, but in much more general fashion. I have changed the title on origins. Okay? That means we start here. Because we really come from the origin of the universe. We don't come from ancestors and so on. We come much earlier. And this is now, I read cosmology. I'm not a cosmologist, but it's extremely exciting what happens there. After the Big Bang, the universe inflated by 10 to the 78. No, representing that? In 10 to the minus 32 seconds. That was inflation. And after that, physics was already there, but it took over, and this universe evolved. Generated particles, generated association of particles, atoms, and the atoms then generated molecules. That's the age of physics, no chemistry. But chemistry started at some stage when it was complex enough, when atoms began to make molecules. Molecules were modified themselves, and they modified by non-living ways. The age of chemistry started about here. Then molecules became more and more complicated, they associated, they began to make aggregates, and the aggregates eventually made some empty aggregates which filled up or whatever. And then a new thing appeared on our planet, life. We heard this morning fantastic illustrations of what this can happen, how it can happen. And that's the time of biology. But it wasn't finished at that time. Luckily, it was not finished because, very importantly, another evolution came up which led to thought represented by the thinker of Rodin. That are steps towards complex matter. Let's have a look at some of those steps, taking it from the beginning. Of course, I will not tell you the whole story because it took 13.7 billion years to tell it, so that's a bit long. Now, science is the human activity which will give us an answer. It's the only human activity which gives us an answer, and I will have another comment on that. That's not an empty slide. It's just a slide which shows that right now we know that the universe has 68% of dark energy, 27% of dark matter, 95% of darkness. Don't know what is it. But there's 5% of visible matter, and that's the matter that matters. We are part of that. We are sitting here, and we know all this. Isn't that fantastic? 5% has come to this point. Now, what are the bricks of that visible matter? These are the bricks. All of you certainly know this. But it took me time to realize what it means. It means that these are the bricks up to uranium, not beyond. Up to uranium of visible matter. There are no other bricks in this 5% visible matter. This is very dogmatic. I am very perturbed when I think about that. But there are no other bricks. Everything in our universe is, in the visible matter in our universe, is made of that. A water molecule is the same here, and it's the same billions of light years away. It's the same. Methane is the same. All the other molecules, if they are produced, they are the same. So it's rather limited. We spoke about complexity this morning. Complexity comes then out of multiplicity, because there are many atoms. But complexity doesn't come out of the building stones. Building stones are those. And that's the playground of chemistry. Chemistry plays with that. Chemistry handles them like children took Lego, build houses with given building blocks, which you can only assemble a given way. And these building blocks you can only assemble a given way. You know that, you are chemists. So you know how these things can be connected, but you cannot connect them in any way. There are specifically very specific ways in which you have to connect them. So the big question then is, a very big question, how does matter become complex? From the elementary particle to the thinking organism, it may be are there higher, even more complex forms of matter. How can you understand this, or at least know about? Physics deals, if you consider scientific fields, we mention only three. Physics deals with the laws of the universe. That's the answer to the question, why? These are the laws. Biology deals with the rules of life. This is how. They are not laws. The laws are given by physics. Biology, living complexity, comes from the way things get put together and how it functions. Now, what is chemistry doing? Chemistry has, in my opinion, a very, very important role, is to build up the bridge towards complex matter from the why. Is it like that? How is it functioning? And this is by self-organization. I mean by that our universe has such a structure that it will self-organize. And we may even call that a cosmic imperative. Our universe has a structure that, in cosmic terms, in the large scale, will organize. So, the chemical evolution of matter was much before Darwinian evolution. You hear a lot about Darwinian evolution, of course, very important for us. But before there was Darwinian evolution, there was a purely prebiotic chemical evolution. The self-organization of non-living matter, that is the evolution, progressive steps in ways which can be understood by thermodynamics. We don't know all the building blocks, but we know the rules. And so the self-organization of living matter was then the Darwinian evolution. I wonder, in fact, if for monocellulars it exists. That is an interesting question. So steps towards complexity, if you take it from the beginning, first of all, there are atoms. With atoms to make molecules, okay? They are linked by strong bonds. Once you have molecules as individuals, this next question is what happens when they get together. And this is the field of assemblies of molecules, of populations of molecules, of a sociology of molecules, supramolecular chemistry, where the interactions are the ones between molecules which can interact and which can build up then entities made of many, many molecules, like living systems, very complicated, many assemblies of many molecules. And then the next step, one can study is how do these things organize, what are the rules by which they organize, and it's spontaneous, but it's controlled by the information stored in the molecules, their structure, the type of atoms they are made of, the way they can fit together, and so on. Now, an example of that is the assembly of a virus. A virus is not living, as you know. A virus, nevertheless, assembles spontaneously, which means it is structural chemistry, it's thermodynamics, it is analytical chemistry, you have to look at it, and so on. And so, for instance, the tobacco mosaic virus is made of 2,130 protein subunits, building blocks. They spontaneously get together and form a sort of a tower, which has, I received, thank you for the green thing. So there's a tower which has a hole in the middle where the RNA of the virus gets in, and the RNA of the virus sort of regulates the length of the tower, the height of the tower. And this is spontaneous. Even, it looks like magic, but it's not magic at all. In fact, there is even a video you can see on, you can find on the internet, where a group has taken large-scale models, just pieces of plastic, having the right shape. You put them in a beaker, and you shake, and you get a sphere. Because they had put little magnets just at the points where they can attach to each other. So this is, in some respects, rather simple. So it looks like a programmed chemical system where the program is in the structure and in the way they interact. So chemistry, from molecular to supramolecular and to self-organization, can be designed. And this is at the hand of chemists, using molecular information, programming the system so that they can interact in a given way, and leading then to functional entities. Next step in complexity is to try to make the system choose what it needs to build itself up. This is introducing the idea of selection in a chemical system. In order to select, you need to find out from a diversity of entities which are the good ones meaning to get the final compound. You need diversity. But you also need dynamics, meaning by that when they assemble, they shouldn't stick together too strongly. Because if the first collision is not the good one, that means thermodynamically, for instance, then you have to be able to go back and try something else. And this then leads to a chemistry which can be called dynamic in its constitution. The constitution of the chemical object, be it molecular or supramolecular, is dynamic, can break apart and rebuild itself. This allows for adaptation. If the conditions change in the meantime, the object can adapt to it. That is why a step in chemistry which is beyond the supramolecular chemistry is adaptive chemistry. Now, this supramolecular chemistry, from the moment it was worked on, understood, is obviously a chemistry which is dynamic in its constitution because the interactions between molecules are rather labile. So the molecules can break apart, the supramolecular entities can break apart and reform. And this can be called the dynamic non-covalent chemistry. But then you can also dream of making what organic chemists don't like, making molecules which break apart. We are trained all to make molecules which are stable. And if they are not stable, you put them in the fridge to calm them down, to sort of prevent this decomposition. But if you introduce reversible covalent bonds into molecules, they can also be made dynamic. And this is a dynamic covalent chemistry. When you now want to put together these two levels of molecules and supramolecular entities, you can define a chemistry which is dynamic in its constitution. The constitution of the object, which can be molecular or supramolecular, and allows then for adaptation because it can change by it can change its constitution by exchanging components inside the object. And then this is a way towards adaptive chemistry. Now, I have to become a little bit technical. Not that it is, I want us to show what kind of reactions can be used, but you can forget it, in fact, because it is the process which is important, it's the concept. A very simple, a very broad chemical reaction is the formation of imines, a CN double bond. This is valid in synthetic organic chemistry, but in biology there is also this type of reaction. And so when you condense an amine with a carbonyl, you get a CN double bond, which can break apart and reform, and break apart and reform. Another one is the one we have found recently, some years ago, where, and don't be afraid, but those are not chemists, by the fact that this is looks like a complicated reaction, but it is a reaction by which this compound, an imine, interacts with this one to form this cyclic system, which can then break along 1,3 or 2,4. If it breaks about 2,4, it goes back. It's a silent process. If it breaks about 1,3, it exchanges the group AR1 against AR2. See? AR2 here, AR1. And that is a way to introduce this possibility to adapt, to lead to an adaptive system. I need it at the end, not so much because that's a reaction, but because there is a process there which is, I think, a very important one. Now, what is this dynamic chemistry good for? It creates libraries. That's a good name for what in the ancient times one calls a horrible mixture of compounds, which you could not treat. Now we have the technologies which allow to analyze this kind of complicated, what now are called libraries, and a nice name for what was considered as a mess. And this can be, it creates dynamic diversity, and it can then be directed by recognition processes between the entities. It has been used for searching for biologically active substances. I will give you an example of that. Just one slide. Dynamic nanodevices, which I will not mention further, and then dynamic materials. This I will give you some examples. So, furthermore, if you see that diversity is recombination, and if recognition is information, so you combine two very important type of characteristic features, combination, diversity, and merging with information. Adaptive chemistry is a chemistry where changing the environment, changing a phase, for instance, organic or water, aqueous, physical stimulus, light, pressure, heat, or chemical effectors, or even change in shape, can lead to changes in the constitution of the object. And these adaptive systems then have one especially interesting feature, which is they can be driven by organization. And that will be the end of my presentation. Can the ability to organize lead to selection of what leads to organization? Now, in terms of looking for, let's say, biologically active substances or specific interactions, starting with components, which are the bricks, if these components are fitted with the black dots, which represent reversible functional groups or interaction groups, where things can build up and break apart again, that means the mixture will give rise to a set of constituents which are all the time in exchange. So we get the bricks, the houses made from the bricks, but houses which can dissociate, reform, dissociate, and reform. So the question then is, what can you do with it? You can use, again, a very simple law of thermodynamics, which is the Le Chatelier principle. If you add a receptor or some kind of a molecule which has a cavity, it will probably have a better interaction with a given combination of the bricks you start with a given constituent, which means that it will bind it, and by binding it, it will amplify it, and therefore select among this set of possibilities the one which fits best. in terms of Emil Fischer, the lock and the key. The lock assembles its key. You don't have to make it. The lock does thermodynamically the driving to finding out which in this mixture is the best fitting entity. And this search for the best binder then has been applied to the search for enzyme inhibitors. It has been applied also for specific architectures which can be produced in this way. And of course, in drug discovery, you can think of using a given target to drive a system, a sort of a library of systems, which could be, in principle, a universal library, where then the target pulls the system towards generating what fits best, the cavity or whatever, some kind of a feature of that target. That's the adaptation to a receptor site. Materials can also be subjected to this kind of processes, and a given category of materials would be polymers. Dynamic polymers, which I may call dynamers. They can be either covalent or molecular, or non-covalent supramolecular. For the covalent ones, the monomers you have here, this and this, they can connect by a reversible reaction. The red and the yellow parts are just functional groups which can connect and dissociate, reconnect, and dissociate. On the non-covalent level, it's the same picture, but now what happens between the entities is pardon, wrong one. This is now an interaction, a physical interaction. The first case, the covalent, is chemical reaction, and this is a physical interaction. Now, supramolecular polymers are interesting in themselves because when you have molecules which can bind together by some hydrogen bonding or some other type of interactions, then you can get perhaps a new class of polymers. And this has been done. We have, the first paper was in 1990. I mentioned that because as sometimes you get very surprises in what one is doing, because, you know, in science, the shots can come from anywhere. There is a group somewhere interested in what has been published. That is why it's so important to spread scientific knowledge, because there are people who might be interested in it and have another idea than you have and get into something very new. And indeed, a small company in the Netherlands developed supramolecular polymers 23 years after we had proposed this idea, and made biomaterials out of them, which have been used for cardiovascular implants for children who needed cardiac reconstruction. And here is the first case, a young girl at that time, 4 years old, Dominica. She had only one ventricle, so I had to separate, of course, because the bloods were mixing. And she was operated by Leo Bukiria in the Bakulev Center for Cardiovascular Surgery in Moscow. And this is 3 months after the operation. You know, both of them are happy. She was happy because she was saved, and he was happy because it worked. And we were very happy too, of course. This is one of those unexpected results. Many children have been now operated, and the Xeltis in the Netherlands also then made heart valves, and they continue their work. It's supposed to be a breakthrough in surgical practice, and this, of course, it makes us very happy. Now, another property of these supramolecular areas is that this morning we heard about self-healing. I think it was Ben Feringa who talked about. Here we have a film which is very, very nice. You almost don't see it. It's very transparent. It doesn't deform the object here. So the 2 fingers you see is my postdoc, Nabarun Roy, who holds it. He made the film, and somebody cuts it in 2. Cut. You superimpose the 2 ends, and you press with your finger, which is not high technology. Huh? It's just pressing with your finger, but it's sufficient. You can now take it in your finger, stretch it, and it sticks. that takes 5 minutes. And after 2 years, it still works. I was a bit surprised, but it still works, because he kept the sample, and 2 years later, he looked at it. Let me get, this is not just technicalities. Now, another property of interest is also, if you have these polymeric, these materials, where bonds can break and reform and break and reform, of course, they can do the self-healing, but they can also change their properties. And let's look at the optical change. Seeing is believing, as one says. So let's have a look. This was done with collaborators who had been sent to my group by Mitsui Chemicals. And they then were developing the basics of it. And Mitsui in Chiba in Japan was trying to see what applications one can get from it. So let me show 2 films. One is made of monomer A, and the other one of and the monomer B. And they make a polymer AB, 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 AB. You take another film, you make a change A prime and B prime, and they make a polymer A prime, B prime, A prime, B prime, and so on. So these are 2 combinations, A, B, A prime, B prime. If the links between A and B are reversible, labile, then, of course, they can break apart and reform, but they can also exchange the A's with the B prime and the B with the A prime. And then, if one of these new combinations has a color, you will see it. If one of these new combinations has a fluorescence, you will see it. So my Japanese co-workers, they like these little pictures. This is a cat head. The head and the ears as AB. The mustache, the eyes, and the inside of the ears is A prime, B prime. You heat, color, and fluorescence very superimposed. So that is a way to show that, okay, you can introduce new properties into this type of materials just by exchanging the components and superposing them. For instance, you could think of writing in 1 dimension with a heating laser, or you can write like a millefeuille in 3 dimensions by then making a stack of them. Now, an interesting experiment about the type of factors which can influence what happens in the chemical entity is shown here. Taking a long chain aldehyde with 3 different diamines, with 2 carbons, 6 carbons, and 12 carbons between the 2 amines. You mix that together, and you look at it in a solvent. But see, not interesting, quite boring. It gives a mono derivatized, just a single imine, not even a diamine, and it's a mixture. So not only it's not complete, but it's also a mixture. So not very interesting. But then you do something extremely simple. You take a drop of that, you deposit on a graphite surface, and you look at it by scanning tunneling microscopy, which in the group of Paolo Samori, one of my colleagues, was done. What do you see? A very nicely organized layer of molecules, which are all these molecules are now bis imines, as you can see, and only the C12. What does that mean? That means that a simple deposition on a surface introduced the adsorption forces which were the best for this C12 bisimine. So it just had the effect of driving the reaction to completion and driving the selection of one of them. And if you look at it, it's really horribly simple, because it's just adsorption, the physical forces of adsorption on the surface lead to the completion of the chemical reaction and the selection of one of the entities among those possible. Now, this is an adaptation to surface adsorption. It's a self-organization drives, self-organization on the surface, on the layer of molecules, drives the selection. One can even say that this kind of process, I don't claim anything about origin of life. It's very complicated, as we heard this morning. But it's a process which is important because a simple process like a physical adsorption can drive a reaction and can select for the components of this reaction. Now, these entities which are dynamic, they make complicated sets which always exchange their components. So once you touch one of them in a physical way, this touching tells the other one, but this one has changed. So if, for instance, if a given combination increases for some reason, all the other ones know, they are connected in a network, that this has happened. So we can try to analyze this network, and I will take by far the very simple one, which is just 4. Having A and A prime reacting with B and B prime to form AB, AB prime, A prime B, and A prime B prime. 4 is what network? A square, very simple. And you put these constituents now on the corners of the square. On the edges, you see that are linked constituents which share a component. AB shares A with AB prime and B with A prime B. So if for some reason some force is applied or some compound is added which amplifies AB, this can only happen at the expenses of AB prime and A prime B. Okay? So you amplify AB. But this then liberates A primes and B primes to make A prime B prime. So what does it mean? It means that on the diagonals, you don't have antagonists where the amplification of one leads to the decrease of the two which share components. But in this case, they don't share the components, so they go the same way. In other words, the amplification of AB leads to the amplification of A prime, B prime. These are agonistic relationships, which means that the action of physical stimuli or chemical effectors lead to that changes in a complex network. And the most important conclusion there is, of course, it's very simple in this case, but it's also adaptable, applicable to more complex systems. Agonist amplification. The fittest for a given perturbation, like for instance adding protons or adding a metal ion, also amplifies the unfittest for that. In other words, there are cases, the agonistic relationships, they make the best and the worst evolve the same way and amplify. Now that is, I can also look at this in terms of development biology. There's something there too. But I could give you examples of that. So these are adaptive chemical networks. And let me just give you a very simple example of that. These are ligands for metal ions, small molecules, which will bind metal ions. If you add a metal ion to that, the metal ion will amplify the one which binds best, which makes best the coordination to the metal, and also amplify the one which is the worst binder for the metal ion, so that you end up with, from a statistical distribution of 25% each to 50-50, the best and the worst. And this is an adaptation to the addition of a metal ion, and you then get, you can represent it by this scheme we have shown earlier. By that adding the metal ion, you amplify AB and you amplify A prime, B prime on the other hand. That's an adaptation. Again, I like to repeat that because I find that agonist amplification is a very important process. The fittest amplifies also the unfittest because there is no competition. This can also happen. What is very important here also is that if you have a very complex setup of a library, at some stage in the evolution, you must, in order to avoid the complexity explosion by having many more components, you have an enormous explosion of constituents, of number of constituents. Then at some stage, you must create compartments. So just to give you an example, you take a solution of components in acetonitrile water. And these components, they can be either lipophilic in red or hydrophilic in blue. These are the ones we use. I don't want to go into the structural details. I want just to illustrate the concepts. And they have a certain distribution. Now you do something extremely simple. You add sodium chloride, and then the phases split, because the addition of sodium chloride makes water and acetonitrile split. In other words, you will get something which is rich in organics and poor in aqueous, and the other phase, which is watery and not much organic. And the result of that is that you get now a distribution between the two phases where the physical nature, the fact that one is organic, the other one is aqueous, amplifies the lipo, the red, and in the top phase, and the other one, the hydro, the two blue units, in the bottom phase, which means the simple separation of two phases leads again to a selection and to driving the system to a given selection. This is interesting also in terms of representing information in chemical systems in another way. If you start with a mixture of these four units, which are represented here, that's the initial distribution. Now, you add to that an effector on the top phase. This will rearrange what happens on the top. And what remains to go to the bottom in the other phase will be changed. So if you like a Maxwell demon, you were sitting on the bottom, you should just look at what comes down and you know what has been done above without going there. It can be done with one, it can be done with another. In other words, the information about what is happening in another compartment is in a distribution, not in a specific interaction. We have spent many years in trying to understand molecular recognition, but here there's no molecular recognition. It's just a distribution which carries information. A given distribution characteristic of what have been added. And when you add different metal ions, for instance, you get distributions which are characteristic of iron, cobalt, copper, manganese, and so on. So information is in the distribution, and there's an adaptation without a message transfer, without messenger. The message is transferred via a distribution. Now, I come to the last example, which uses that complicated reaction I showed. I'm very interested in that reaction because it is a metathesis reaction without metal ion. It's a purely organic metathesis. This is for the chemists here. So this is this process which I showed, where you exchange the blue with the red, just by combination in this four-membered ring, which can split one way or the other way. Now, the unit here is called a barbituric acid, and that has been studied a lot, for instance, by David Reinhardt and many other people, but he did very nice work on that in the Netherlands, and showed that it forms a nice rosette. That means 6 of those things can form a macrocycle where the units are linked by hydrogen bonding, so it's a supramolecular macrocycle, which is formed like a nice rosette. Now, once this thing is formed, which is sort of a flat ring, they can pile up. And they then lead to a type of supramolecular polymers which are columnar, not linear, but columnar, which means it goes there. Okay? So you mix them together, and the system will automatically first combine, assemble the 6, and the 6 will then pile up. So the system is driven to form the final columnar entity. And it happens, which can be easily guessed, that at the beginning, if you have a solution, at the end, you will have an assembly which can lead to a higher organization than a solution, which is a gel. A gel, a confiture, a jelly. And that is more organized than a solution. Now, what can you do with that? Can this formation of a more organized system drive the selection which leads to the organization. So a sort of a catalysis of self-organization. Here are 4 constituents formed each by 2 components, so they can exchange. One of them has been designed and synthesized in such a way that this one, the green one, forms a gel. The other ones, the other 3, that means that one, KN1, KN3, and A1, KN1, A3, and A1, they do not form a gel. But the KN3 forms a gel. That's the one which will lead to this higher organization. So what is happening? A way to study that is you can do viscosity, you can measure viscosity, but it's much better to do nuclear magnetic resonance because there's a property of in NMR signals. The line width shows how mobile the molecules are. And that is a way to look exactly at the molecule, what it is doing. And if it is getting jellified, it will move more slowly. So the line has a wider width. And this is an easy way to measure intrinsically what is the mobility of the molecule. So if you now, what is a simple way when you have a gel, when you have a, as I said, a confiture, when you heat it, of course, like honey, if you heat it, it gets fluid. And if you cool it, it gets more and more and more sticky. So you can, here you see on the right-hand side that the line width of signals in this NMR spectrum will decrease if you go into the region where it is melted. It is broad lines in the gel and in the solution, narrow lines. So what does that mean? That means the following, that if you go from high temperatures here to lower temperatures, you go from a solution, sol, to a gel, and this then amplifies the one which forms the gel. At the same time, it amplifies its agonist. But the important thing is that the formation of the gel, the formation of organization, drives the system to make the entity which is organized. And then comes the next step. If you get too many components, you have a sort of a constitutional explosion, and then the phenomenon may be washed out by the fact that you have too many entities. And there comes in the necessity for having compartments. At some stage, if one wants to go to more complex systems, there must be compartments. And we heard this morning about primitive cells, the proto-cells, the approaches through formations of liposomes, formations of micelles at the start, to select for given entities, which then are selected and taken out of the total mixture so that you do not get this combinatorial explosion, which would wash out all the characteristics. So if I represent that, at the beginning, when the system is in a solution, that means very mobile molecules, you have almost 25% of each. Distribution 25, 25, 25, 25. You cool down, a simple change of temperature, nothing complicated, simple change of temperature. You get a strong amplification of that one because you now form the gel. So this means that there is an amplification of the one which wants to be organized or which is organized. At the same time, of course, of the one which is the worst in organization. So the order increases in this way. By heating, the order decreases. So if one wants to be forward-looking, one can say that if organization can happen, organization will happen. Or phrased differently, if order can be, order will be. Thermodynamically driven. No secret. Thermodynamics rule the world. One can even say that in our universe, it's probably a cosmic imperative. That if something can be organized, there will be some conditions where it will happen, where organization will occur. It may be, and I'm convinced it is, an intrinsic property of visible matter in our universe. That's a strong statement, but I think our universe, which is a rather simple thing, not living systems, because multiplicity makes things more complex, but the basic building blocks are rather simple. DNA has only 4 bases, makes 2 base pairs, and that's enough. Amino acids, 20. Why only 20? Because it would be chaotic, would be difficult to keep the information, so simple is better. Now let me conclude by some general remarks, but I think that is my most important remark here, by far. I would like to cite a mathematician, David Hilbert, very famous mathematician who worked in Göttingen. He wanted on his tombstone to be written 2 sentences he had once used in a talk. We must know, wir müssen wissen. That is a strong statement. Wir müssen wissen, we must know. But the second part is even stronger. That's a vote of confidence. Wir werden wissen. We will know. That is science. I guess that is why we are here. That's what scientists want. The push for knowledge and let's say the intimate conviction that we will get there. Prometheus stole knowledge from the gods and gave it to mankind. The fire of knowledge, and here he shows the fire of knowledge, which is science. Science makes us able to know. And for all of you who are looking forward to your future, science shapes the future of humanity. It participates. How do you transfer science? We heard this morning about Lucy and evolution. Okay. Yeah, there is some transfer of knowledge between generations and in the course of evolution. In the present, Michelangelo, touching by the fingers. In the future, we talked also about robots and all that stuff this morning. I don't think that it will be very agreeable, at least for us, to only shake hands with robots, but we are already modified. Some of us have other, let's say, have some titanium in their hips. They are modified. You have other teeth, implants, we are modified, and can even be much more advanced. If you get a heart transplant, you cannot say to your spouse anymore, I give you my heart. It's not yours. So I think we have to take these things in a way where we shouldn't be attached just to the way we are. The universe will evolve, we will evolve, we will adjust to it, we will adapt to it, and we shouldn't say the way we are is good. Well, let's see the future. The last point I want to make, and I see over time, but not too much. Here is our planet on which we are sitting. A piece of dust in an enormous universe. But on this dust, there are these people here in this room. These people sitting on this piece of dust understand much, by far not all. Maybe it's just at the beginning, but it's quite incredible that sitting on this thing, turning around in the universe, being able to know what are the bricks of visible matter in our universe, what are the basic processes, physical processes, thermodynamics, which drive the organization of that universe. And finally, for all of us, I think it's really very important that science should have, must have, and has no borders. Science has no flags. Science has no borders. Science has no dogma. Science is the only, I stress it, the only human activity which is valid everywhere. If you someday can go to a distant galaxy, a water molecule will be the same. It's a bit disappointing to have these limitations, but that's the way it is. And a two-legged beast on this piece of dust has been able to think that, thanks to science. I encourage you to practice science. Thank you very much.